Day 2, we have the units and measurement we'll talk about today in this video. Alright, so first of all, chemistry uses the SI system, or the System International units. Alright, so what does that look like? Well, there are some fundamental units, right? And these are fundamental because they're just defined. So mass. When we talk about mass, right, this is how much matter. Right? How much matter. Now, weight and mass are the same on Earth, right? But weight has to do with the acceleration of gravity to an object, whereas mass is how much matter is actually present. And so we use the kilogram, which is the only one with the prefix, and we'll talk about the metric system prefixes soon. Right? So you got mass, you have kilogram, and that's the symbol kg. Length, right? That's a distance, space between 2 points. Meter, all right. Time, second, right? You guys know what a second is. Temperature, we actually use Kelvin. Now, a lot of times we'll use degrees Celsius because the size of a degree Celsius is the same as a Kelvin. Volume is the liter, and that's how much space. Right, so length, length and distance. Time, duration. Temperature is thermal energy. Volume would be space. All right, and that's in 3Ds. Amount of substance, which we'll get to later. Moles. Think, particles. Electric current is amperes, and that's more of a Chem 2. And then one we won't use at all is luminous intensity, candelas. Now some derived units. All right, velocity, change in position over change in time, meters per second. Most of us in the United States are used to miles an hour. But meters per second is the velocity with SI units. Then you have acceleration, which is the change in velocity over time. So meters per second squared. Force, newtons, so this is a newton. Newton's second law, mass times acceleration. So you have a kilogram, right? Meter second squared is a newton. Work and energy have the same units. So force times distance is work or energy. Alright, and so this is a kilogram meter squared per second squared. So, for an example, if you have an Nalgene bottle, that's a 1 liter bottle, basically 32 ounces. 1 liter is a little bit right around there. It's a 32 ounce bottle, but it's really close to 1 liter. Alright, if you take that and you move that, you accelerate that Nalgene bottle full of water, the distance of 1 meter, that's basically a joule. Alright. Then we have power, which is energy per time, which is kilogram meter squared per second cubed, joules per second. So this is a joule. Write it down. Watt. Alright, that's why our electric bills come in a power company, because they're in kilowatt hours. Alright, now pressure is another one. It's force over area, where you have force, right? Kilogram meter per second squared divided by area, which is a kilogram meter second squared, or Newton per meter squared, which is a Pascal. Now we don't actually use pascals. We use atmospheres, and when we get to gas laws, we'll use atmospheres. Frequency is 1 over time, cycles per second. Alright, rotations per second, whatever you want to talk. It's hertz. H-E-R-T-Z. It's hertz. Alright, and so now, alright, it just has to do with waves, and we'll get to that in chapter 2. Alright, so those are the common derived units, our fundamental units, and so those are the units we will use in this class. All right. Now we will use other ones. We'll still, use some English one, but most of the time we'll be using the metric system because that's what the universal language is of science. All right. Now our current book goes into energy, and they define energy as the capacity to do work. Well, that's okay, it's true, but a better definition is kinetic energy to the motion of the particles that compose a sample of matter. Alright, so everything you have, every piece of matter has this stuff called thermal energy. Right? The particles that make up the matter, we haven't talked about those particles yet, but the particles that make up the matter are actually in motion. Now sometimes the motion is just a vibration or a rotation. Does not have to be moving across the table. They can just be moving, right? And like if you can't sit still, your legs are moving or something. You're not really moving relative to your chair, but you're vibrating, right? And so this energy is a random, incoherent motion, right? So it's not organized at all. It's just totally random, and we call it thermal energy. If we heat a sample, we increase the thermal energy. All right, and temperature here, temperature is the measure of the average thermal energy of a sample of matter. So temperature measures this thermal energy. All right, temperature measures the thermal energy. All right, and we'll talk more about this when we get to the thermal dynamics chapter or thermochem chapter, but thermal energy, right, is how much energy a molecule has. Heat is the collection of thermal energy. So temperature and heat are not quite the same thing. There's a law of conservation of energy, which energy is neither created nor destroyed, and the energy of the universe is constant. All right. So your book dives into energy here, probably because they're just doing units with watts and whatnot. So we're going to cover it real quick. Now, with temperature, all right, the concept originated with Galileo, believe it or not. Right? So the first air thermometer was in 1612, and then we have 1654, an alcohol thermometer, still no scale. And then in 1714, you might recognize this guy, Gabriel Fahrenheit. All right? That guy. Degrees F, perhaps, right? Came up with the mercury thermometer and a scale. In 1742, Celsius invented his scale. All right, and then 1848, Lord Kelvin came up with absolute temperature. All right, and so if we look at water, the boiling point, so BP would be boiling point. Boiling point of water, Fahrenheit's 212. All right. Celsius is 100, and Kelvin's 373. The melting point, right, 32, 0, and 273. So let's talk about this. So Fahrenheit came up with his scale, and he used 0 and 100 for his references. 0 degrees Fahrenheit is where a saturated solution of salt water freezes. So those of us who've been driving in wintertime on cold roads with maybe snow, ice, a lot of times local municipalities will put salt on the roads to help melt the snow and the ice. Below 0 degrees Fahrenheit, the salt doesn't work anymore. All right, water will freeze. All right, that's good to know. Okay, so that's where he made his 0. Now his 100 was human body temperature, 98.6. That's pretty close to 100. So that's where he came up with his scale. All right. I don't know why he picked it. I don't know that. I just know that's his scale. Celsius, he used water. 0 degrees when water froze, 100 degrees when water boiled, and used that. All right. Now Kelvin came along and found where molecular motion stops. So this is where molecular or particle motion stops. So there's no more movement of the particles. So he used the same scale as Celsius. He just made it so it's always positive. That's why we say absolute temperature, no negative. So that's negative 273, negative 459. So that's the temperature scales. All right. Now we'll move on to the metric system. All right, the metric system. And all the metric system is a system of prefixes to help us read and compare numbers to each other. That's all the metric system is. And we're going to use the metric system just where we need it to be. If that makes sense. So, right. If I'm 100, well, let's put the metric system down, and then we'll put it down. So we got the base unit here. So this would be the base unit. All right. This would be grams, liters, meters, anything you want to use. All right. It can be bytes for a computer. It could be donuts. It doesn't matter what it is. It's that dollars. Right? It does not matter. That's just the base unit. And so if we go bigger, all right, if we go bigger, the first one we really talk about when we go bigger, right, is this one in kilo. It's a lowercase k, and it's 10 to the third. Well, let me do it this way. 10 to the third, and that's kilo. All right, 10 to the third is kilo. Now, are there other ones in there? Yes. Right, there are actually other ones. And so, do we use those other ones? Not really. All right, and so not really. So we like to. I mean, there's deca and hecta or hecto. Excuse me. All right, there's deca and hecto. We don't use those much. So do I have? I just put. It's a lowercase h and a da. We won't use those in class. They exist, but we won't use them. And then there's 10 to the sixth. We use 10 to the sixth, and that's mega, capital M, mega. And then there's 10 to the ninth. All right, and 10 to the ninth would be capital G for giga. Some of these you probably have heard of with computers, right? And then we have 10 to the 12th, right, which is tera. And then we have 10 to the 15th, which is, I think it's peta. All right, and so those are going bigger than 1. Going smaller than 1. All right, we have deci that we won't use. We have one that we use all the time in centa. All right, 10 to the minus 2. Centa. We use centimeters all the time. And then we have 10 to the minus third, which is milli. Milli. Right, milli. And then we have 10 to the minus 6, which is a Greek letter mu. It's a Greek M for micro. We have 10 to the minus 10th, or 10 to, excuse me, minus 9th, which is nano. And then there is there is right here 10 to the minus 10, which is an angstrom. Oh, you can't really see that. That's an angstrom. It's an A with the 0. It's an angstrom. Then we have 10 to the minus 12th, which is a P for pico. It's a lowercase p. So the green p over here is an uppercase. That one's a lowercase. And we'll do 10 to the minus 15th, which is F for femto. Alright, and so those are the prefixes. Alright, and so if somebody happens to be 179 centimeters tall, alright, if you're 179 centimeters, right, that's the same thing as saying 179 times 10 to the minus 2 meters, which is the same thing as 1.79 meters, because we do the scientific notation, right? Okay, so now measuring humans, most humans are between 1 and 2 meters tall. Some are more than 2 meters tall, but most are, adults are a meter tall. It's a little over 3 feet. So most of us are between 1 and 2, definitely between 1 and 3 meters tall. All right, and so that's accurate. Now the same thing, 1.79 meters, right? We can write that as kilometers too, couldn't I? I could write that as 1.79 times 10 to the minus 3rd kilometers. Alright. Why would I do that? I have no idea, but you could, right? Because it's the same thing as 1.79 times 10 to the negative 3rd. Kilo means times 10 to the 3rd. That didn't change colors. Times 10 to the 3rd meters, right? And they cancel out, right? We wouldn't probably do that, right? But you could. All right, some other measurements you'll see a lot this semester would be like 475 nanometers. All right, so if I have 475 nanometers, that's the same thing as 475 nanomeans times 10 to the minus 9 meters. That's the same thing. Alright. Just like if you had a 5K. 5 kilometers same thing as 5 times 10 to the 3rd meters. Right? And so all this is the prefixes tell us where we're at on here, right? So all these examples I've used so far are distance, meters, right? And so we're either a fraction of a meter or we're bigger than a meter, right? So kilometers are multiple meters put together, right? Centimeters are a fraction of the meter, right? So 179 centimeters is 1.79 meters. It's 1 meters and almost 80% of another meter. All right, and so all that metric system is or are these prefixes that help us compare numbers, because we like to compare numbers between 1 and 1,000. Very easy for us to do. All right, we do. It's easy. 400 is bigger than 200, right? 45 is a bigger number than 7. Right, we do that. But if you have really, really big numbers or really, really small numbers, right, and it's sometimes hard. And we like to keep it the same prefix because a lot of times, like if you watch news, I don't usually watch the news, but if you watch the news and somebody says 45 million and somebody says 3 billion, we compare 45 to 3. But 45 million is right there. 3 billion is right there. That's a huge difference in money. All right, but they don't do that, right? There would be 3 billion would be what? 3,000 million. And so that's it's weird, but that's a better way to compare it, right? Because we want to compare numbers. So when we look at data, we want to compare numbers. All right, so that's all the metric system is. All right, it goes back to the fundamental units of a gram. Right, now kilograms are the base unit, or the SI unit, because for whatever reason. But grams, liters, meters, seconds. All right. Okay, because there are things that happen on the second level, on the kilosecond level, on the femtosecond level even. All right, and so these are just the metric system, so we can compare, contrast. All right, and they're just prefixes, and we'll get good at using them.